This is the lesson video for 4-2 Day 1. For 4-2 Day 1, you're going to add another tool to what you're able to do with derivatives. And the goal with 4-2 Day 1, or this implicit differentiation that we're going to work on, is how to calculate the derivative for an equation that has more than one variable, and maybe isn't even a function to begin with. We want to be able to find the derivative without having to get it into y equals form and applying the ideas that we've used so far. This is most handy for something like what you see, the equation of a circle that's not a function. If I were to rewrite it as a function, it would need to be two separate functions with a y equals plus or minus and a radical. So I'm hoping I can find the derivative and do calculations about it without having to get to that. So implicit differentiation says we're allowed to take the derivative of both sides with respect to x and put in our derivatives as we go. What that's going to mean every time that there's a y term is that I'm going to have to think about chain rule. So as I start to take the equation that was given to me, and if I'm always doing my derivatives with respect to x, as we are, then when I take the derivative of 2x squared, that'll be 2x like it always has, times 1 for chain rule, if you want to think about that. Then when I take the derivative of y squared, it'll be 2y, but I don't know what y's derivative is with respect to x because it's not written in a form that tells me what it's worth in terms of x's. So like chain rule, if this was a u squared, it would be 2 times the u function times u's derivative, 2 times y times, and here's where notation is going to be important, whatever y's derivative is with respect to x, and 25's derivative on the other side is 0. Now as I go to calculate things, I'd really like the derivative in a form where I can just throw the values in. So you're going to solve for dy dx. To do that, I need to first subtract the two x's to the other side. So think algebra. That'll make it negative 2x. Divide both sides by 2y so that I get dy dx, the derivative in terms of x, by itself. And it tells me I'd have to take 2x, the opposite of it, and divide by 2y, and when you simplify it, it says it's going to be the opposite of the x value over the y value at any particular point. Now that I have the derivative, I can go applying that to see what the slope at the ordered pair 3, 4 on this circle is, and when I look at the ordered pair 3, 4 on this graph, looks like my derivative needs to be negative, and again, maybe negative 1-ish, a little hard to read off the graph accurately. So we're not going to try to read it off the graph. We're going to apply the derivative and find that slope. So then the slope at 3, 4 means I need to take and evaluate the derivative there. And this is the first time we've needed both values of the ordered pair in order to evaluate the derivative. Keep in mind this isn't a function, so at 3 there's more than one ordered pair. And the slope would be different at these two different locations. So opposite of x over y evaluated at the ordered pair 3, 4 is what you could use as your notation to tell what it is you're doing in your work. So that will be negative 3/4 as our slope at 3, 4. So the next slide is going to give you some basic steps for this kind of differentiation. So pause the video, take those as good notes so you have them, and then we'll practice with that. So this is the page I'm referring to. Notation is critical here. You want to be sure that you get these notes down, and then as we start to use them, that you make sense of what we're using the dy dx to hold the place of. Pause the video, come back when you're ready to move on. So now we're going to try out those steps that you recorded. We might not need every step in every one of these, so a little patience in that sense. So this is a curve. You don't need to be able to pronounce it. They would like to know the slope of that particular curve at the ordered pair -2, +2. So that's that point right here. A tangent to the curve right there looks like it could be horizontal, or at least very close to 0 for its slope. So the plan is I want to take the derivative of this equation, but it's not in y equals form, and I'd rather not get into square roots and all that. I want to use this implicit differentiation idea. So for my equation that's y squared, the derivative should be twice the y multiplied by, and here's where chain rule comes along, dy dx, since I don't know what y's derivative in terms of x is. The other side of the equation for its derivative will be a lot easier. I'm going to have 3x squared plus 6x. So when I evaluate and move my dy dx to be alone and solved for, I'll get that to find the slope at any point on this curve, I need 3x squared plus 6x divided by twice its y value. So therefore, when I go to evaluate, the original question was the slope at negative 2, 2. Turns out I actually need both those parts of the ordered pair to evaluate this derivative at that particular location. So this evaluated at negative 2, 2. When we plug all that in, and again, go ahead, stop the video, do the calculations, and see if you can come up with the same thing that I do. You end up with a slope of 0, which certainly seems reasonable at that point. The next test asks us to go even farther and to write the equation of a tangent to the curve when x is negative 1. Well, here's the challenge. When you look at the graph, there's more than one place on that curve where x is negative 1. So we're going to have to find the actual ordered pairs involved there. So we'll start with that. At x is negative 1, I see 2 locations on the graph, because again, it's not a function. So I'm going to go to that y squared function, or equation, and calculate what happens when x is negative 1 on the actual curve, not its derivative. And it turns out that you get that y squared is 2. Therefore, the y value at that particular x is the positive and the negative square root of 2. So one ordered pair is negative 1 square root of 2, and the other one is negative 1 negative square root of 2. And those are the two ordered pairs that we've got. Same x, different y coordinates. Now that they want us to find the tangent to the curve at those two places, now I have to get the slope at those two places. So as I go ahead and evaluate that derivative, that 3x squared plus 6x all over 2y, and I'm just going to take them one at a time, at negative 1 square root of 2. I'm taking the higher of the 2 points. And when you plug all that in and do a little bit of simplifying, and take the time to do that so you see where this comes from, and cleaning up, I got a radical out of the denominator and everything. That was the slope I came up with at that ordered pair. So then my tangent at that particular point should be y minus square root of 2 is negative 3 root 2 over 4 times the quantity x plus 1. Oh, that's right. So as we go through and do this, now I'm thinking about, well, what else do I need? Do I have everything that they asked for? Now that I look back, that first one I don't think is right. Nope, we're all good. Okay. Got myself a little worried. So on the second one, we need to go back and get the slope at the other point. And the slope at the other point doesn't look like it's the same as it is at the first point. So at the higher point, negative 1 comma square root of 2 looks like it should have a negative slope, and ours did. But at negative 1 negative square root of 2, it looks like it should have a positive slope. So as I go to plug in my ordered pair, and you guys, again, stop the video, pause it, make sure you've got everything, your slope actually comes out 3 root 2 over 4. So when we go to write the tangent for that one, that makes sense. It's got a positive slope. So we're looking at y plus the square root of 2 is 3 square root of 2 over 4 times the quantity x plus 1. Continuing to use this then, I want to be sure that we've got some of this down, so I've got 3 up here for you to try. I want you guys to pause the video and try the first one, and then come back. So if you're back, we're going to go through that first one. And that first one, we need to differentiate on both sides, so the derivative of x in terms of x is 1. The derivative of sine of y in terms of x would first be sine's derivative, which would be cosine of y. And then we need y's derivative, which we don't know what it is with respect to x. And then I'm solving this for dy dx. So my derivative with respect to x, and you could leave it written one of two ways, 1 over cosine y if you'd like. You could also rewrite that as secant of y. Alright, the second example. Again, pause the video if you'd like to try it out. What I noticed right away about the second one is that on the left-hand side, I know how to handle that. On the left-hand side, I'll know how to get derivative of x, and then I'm going to rewrite this so that I can see the chain rule portion of this with the squared part of the function. Then on the other side, I'm going to rewrite the function to realize I'm going to have to do product rule on that side. So now that I've just done a function rewrite, separate this, now I'm going to go ahead and calculate the derivative. So derivative of x is 1 plus, now I need to think not only chain rule for the y part, but chain rule for the squared part and the cosine part. So derivative of anything squared is 2, keep what you had, to the first power, times derivative of what's on the inside. So for my cosine function, that's negative sine of y. And for the y part, because I don't know its derivative with respect to x, dy dx. On the other side now I need to be thinking about product rule. So first term times derivative of second plus second term times derivative of the first. Wow, I've got a lot of stuff going in there. What I need to do now is gather all my dy dx terms on one side and gather all my not dy dx terms on the other side. So as I look, this term does not have a dy dx, this term does. This term does, this term does not. So as I gather them algebraically on one side, I want all the ones that have a dy dx, and algebraically on the other side, I want all the ones that do not. So I'm going to keep this negative 2 cosine y, sine y, dy dx term on this side. And I'm going to subtract over that x dy dx term, and I could just as easily brought those to the other side. And then I've got a y already on the right-hand side, and I'm going to bring over a minus 1. I'm going to factor the left-hand side so that dy dx is out front, and therefore I'll be able to solve and get it alone. So I'm going to have negative 2 cosine y sine y minus x equals y minus 1. Solving then, my derivative is dy dx. On the other side, y minus 1 divided by the quantity negative 2 cosine y sine y minus x. Depending on which side you moved everything to, you might have ended up instead with 1 minus y all over, and then you wouldn't have had the negative down in the bottom here either, 2 cosine y sine y plus x. Again, algebraically they're the same, either one is okay. Final derivative here. Final derivative is for that x cubed plus y cubed equals 3xy. And again, you could move everything around so that you've got some space. I'm going to need a little here. I'm going to bring that entire function down where I've got a little more room to work with it. And as I start to work with it, again, I'm going to have to notice where I've got product rule in order to get the derivative for that side correct, and be a little bit careful with my other things that have a y in them. So my derivative for x cubed is 3x squared, plus derivative for y cubed is 3y squared dy dx. And on this side I'm going to need 3 times, and again I could put the 3 with the x as the first term, so 3x times derivative of the second term, plus y times derivative of the first term. Gather all my dy dx terms to one side. So, as again, a little highlighting, this term has a dy dx, that term has a dy dx, the other two terms do not. So I think I'm going to keep the 3y squared dy dx term on the left-hand side, bring over the minus 3x dy dx term, and keep the 3y on this side and bring over the 3x squared. Now as I go to solve, I'm going to factor that dy dx from the left-hand side. Again, no sloppy algebra and no shortcuts here. That's where we cause our own problems. So my derivative of y with respect to x is, and here's where I might want to factor a 3 out, because I will eventually need to simplify just to make my calculations simpler. And if I factored a 3 out of the numerator and denominator, I'd be able to rewrite as that. Again, if you gathered it to the opposite side, then your numerator would be the opposite and your denominator would be the opposite. So you might also have, instead, depending on which side you gathered your dy dx terms to, you might have this. All right, so assignment-wise, you've got the assignment here for day 1, and we'll see you soon.